a mistake. Earlier presentation was that I think I did change the first slide. Pardon me. Okay, so using both the data-driven and numerical models. There is the up and down.
Just up and down.
Okay, so when we talk of studying with data-driven models, I think that's nothing new what we are doing in some sense. For a long time, we have been using concepts which are already been there. It's only the data-driven is more like a buzzword. For example, if you're looking at statistics, all the statistical things you are doing, like let's say time series analysis, is nothing but what you are doing in a sense, in a less fancier way, maybe with less data that we had when we were doing with statistical models like ARIMA, etc., etc. They were there for a long time, and people have been using, let's say, regression models to predict something. Let's say even monsoon forecast for a long time was done with regression models. And let's say if you're looking at dimension reduction, which is the other thing that you do with models. One is to kind of do a time series. The other one is if you have huge dimensions, you try to reduce it. So you call it as dimension reduction. And if you translate it to what already all of us have been taught, let's say EOF is nothing but that. It reduces your dimensions. You have a very large dimension model. You want to make it, you want to extract that data out of it. That's what you're doing. So the same concepts packaged maybe with more fancy words and maybe even better forecast, better algorithms than what we were doing. There's nothing but data-driven. Okay. So this is just an overview. How do we model climate and weather? I guess there are multiple components which come into picture. We know that you have energy coming from the sun, you have land, you have ocean, and all the motion that you find either in the ocean and the atmosphere is coming from the energy from the sun. So that's the source that we are looking at. And there are various kind of subcomponents which come into picture. For example, if you have atmosphere, you have motion of the air, and then you will have, let's say, evaporation from the surface, and also you'll have water coming into it, or let's say circulations and heating going in and out, and all the components and all the fancy things that we are looking at, all of them would be in the Earth system. So you will have a motion which will be continuously reacting with the atmosphere. You will have cryosphere, and you're in the polar regions, or let's say hilly regions like our Himalayas, etc. You have the cryosphere, and you have, of course, the ocean, which is circulation, and land, which, if you're looking at it, you can have biota occurring there. All of them will have to come together. And if you look at it in a conceptual way, all of them are they need to interact with each other. And as you are going into the future, you have to co-evolve. Like what happens in the atmosphere affects your ocean and vice versa. So that's the brief overview. And this is a top level abstraction. Those who have done my course, I think this may find it familiar, but you have these kind of, let's say, top level components. You have your ocean, you have ice, sea ice, land, and ice, and then you have biogeophysics, biosphere, etc. The interactions that come from there, all of them we need to take into account when we talk of a climate model or the components that go into it. So this is the hierarchy of models that we are looking at. At the top, you have a very complex models. At the bottom, in one limb, you have idealized models. On the other limb, you are looking at all the data, more and more of data on this limb. That is, at the top, you are looking at fully coupled Earth system models, the kind of models that we use in CMEP to look at future predictions or future scenario simulations. That would be at the top level. Then you may simplify and say I'm not very much interested. I'm looking at something in the atmosphere where I can just do the GCM, the general circulation model. And I may say that I'm going to prescribe the proportion. So you have GCM there, maybe a simplified GCM also. And then I think quite a few of you have done simulations with aquaplanet. So you also get aquaplanet. Lower down would be the radiative perspective models. The energy balance model, finally at the Lorentz and idealized model. If you go on the this plane, which is what we are going to look at, is your data-driven models. At the top, you have reanalysis, which if you're looking at today's major data-driven models that you're looking at, like GraphCast or ForecastNet, any of them, the basis for them is reanalysis, which if you really look at it, it is kind of coming from a GCM. Like you have analysis, you have data coming from satellites, you have a model, more or less like a GCM, where it's kind of creating the analysis, and that is being used here. It's still not that you can say that I'm going to have a purely data-driven model. Even if I use reanalysis, and in some sense I'm using information from the GCMs. But let's say tomorrow I replace it so that the same reanalysis could be done with AI and ML. Then this thing would be kind of independent of the other. So if you go down, then you have the machine learning emulator. Then you may have models which they call as catastrophe models. So let's say for a high rainfall or any other major events. And below that would be the data-driven models, like the one that is we are now talking about GraphCast, etc. So this is the kind of you could say in some sense a pyramid of both numerical and data-driven models. And if you're looking at a system, these are the various components that you have to put in if you have to go into the future, or even let's say for let's say decades. You will need to look at the chemistry from CO2, NOx, etc. Then you have CIs, ocean ecology, biogeochemistry, ocean circulation, plant ecology, if you're looking at land and plant physics and hydrology. All of them need to be combined together and they need to evolve together because they are going to interact with each other. What happens in the ocean or let's say on land is going to affect the atmosphere, and what happens in the atmosphere affects the land. And as you're going into the future, they are going to co-evolve. So that's what we call as an Earth system, which is at the top of our pyramid. So that was a kind of a brief overview. Now we'll kind of concentrate on data-driven techniques. The first question we ask ourselves is, why are we looking at data-driven techniques? And that I think this itself answers it very. Nowadays, from satellites or various sources, you have enough data coming in for climate and weather. And if we just look at ECMWF, I mean, I got numbers only for ECMWF, I'm sure, and SEP and other repositories have data sets comparable or even larger than that. And we have about 450 petabytes of data sitting in ECMWF. And every day, about 300 terabytes are being added to it. So that's the kind of data that's coming in. So obviously, huge amount of data is coming in. And physically, it's not possible for us to look at it and analyze. So I think that's where the data-driven technique comes in, where it automatically picks up connections, etc. within the huge data that you have or the relationships that can be picked up with data-driven techniques. And that's why it is becoming more and more popular. And if you look at it, this is kind of a spin-off. Like you have data coming in not only for weather and climate, in other fields also a huge amount of data is being produced. For example, every time you do your UPI payment, somewhere some data is going in. And let's say you have billions of such transactions, which becomes a huge data set, which can be mined to look at, let's say, patterns within it. Like, let's say if you're in this particular age, this is details you have. Some details, if they're able to get, then they can say that, okay, this is your spending pattern. You may spend more on shoes, less on. I mean, old people like me may only buy chappals or simple ones, but youngsters might buy more fancier things. So all those kind of information, finally they want to know what is happening there. And that's the new algorithms they are building. And when they are building those new algorithms, we can use it to study weather and climate. So in some sense, the other fields are also helping us to improve our weather and climate forecast. And the other one that has happened is computing power, which is basically like the biggest revolution which has come in the last, let's say, about 10 to 15 years is this graphical processing units. That was also like a, would say in some sense, a serendipity. These GPUs were actually started for built for, I think, gaming processors. They wanted good graphics. And they suddenly realized that there's a lot of computing that you can do because in gaming also you have long matrices and vectors, which you have to optimally kind of calculate. This becomes a technique which could go into the data-driven techniques because basically data-driven techniques are nothing but, in some sense, manipulation of huge matrices and matrices or vectors. So that's where GPUs came into picture. And combining these two, now we are able to use it, these data-driven techniques to study weather and climate. So this is a slide I have taken from NVIDIA's presentation to NOAA. On the left, this is how the natural language generation, the number of parameters that's increasing with time, and the size of it, the number of parameters, and the number of GPUs that would be available. So they are now at GPT-3 is, I think, 175 parameters, billion parameters they are looking at. They want to go to 1 trillion parameters. And that is basically the kind of information that we use using a natural language processing like ChatGPT, etc. And so there's a expanding exploding model size. And data is also growing very rapidly. The major sources which they are showing here is the fusion test reactor, fast breeder reactor, which says generates about 50 terabytes of data per day for analysis. Of course, if you're looking at the kilometer array, it is generating 16 terabytes per second. I mean, I don't think you can even think of archiving that way. Maybe only 0.1% of it might be archived. Look at it. And if you come to our domain, about 287 is what NVIDIA is saying, and 350 is what somewhere else I found. So you have about 287 terabytes per day of data being archived. And if you look at this increase, it's almost an exponential of scientific data that's happening. This is from 2010, and we are somewhere around 2024. So it's almost an exponential growth of data is happening. And data is not only growing in our field, but in every field. And in those fields also, they are kind of coming up with newer and newer techniques, which they can exploit and which we can exploit to kind of do study our weather and okay. So let's ask ourselves where we could use data-driven techniques. It could be used for, let's say, predicting weather and climate from past data. I think these words are now buzzwords today. GraphCast, Pangu Weather, ForecastNet, etc. I'm sure all of you have heard of it. They are from various sources. GraphCast is from Google, Pangu is from Chinese group. Chinese are one of the best AI, I think, data scientists in the world. And they have come up with a very fantastic data-driven weather forecasting model. ForecastNet, I think, comes from NVIDIA. And if you look at where we can use it, the simplest would be like you already have a numerical model. You have to take forecast, and you know they are not perfect. And if you have, let's say, you have 25 years of forecast with you, you can use that information, use some data-driven technique to do a bias correction. So that's the simplest way you can use a data-driven model. And it's also being very widely used. Let's say you do a numerical model, take the forecast from that and kind of remove the biases or improve your forecast in the simplest possible way using the data-driven techniques. The second one would be, as we discussed earlier, you could be using AI and ML to create data simulation. Right now, we are purely dependent on conventional models to create data simulation. We could replace that with a purely AI ML based tool. Another area where we could look at is what we call as hybrid models. That is, you have a conventional numerical model, whatever we are already familiar with, and we replace parts of them with AI. For example, you have models, some of them are fairly empirical. Let's say you're looking at top parameterization or boundary layer parameterization. You're not doing it from first principles. It's not possible to do, let's say, boundary layer parameterization from first principles. You always have to do an approximation. And so what you can do is, you can replace it with an AI model. And previously, those, let's say, the boundary layer parameterization or cloud parameterization would be based on some, let's say, experiment. Let's say if it was developed by, let's say, Americans, they would have taken the gate experiment, taken some data from that, and fitted some empirical models, either for boundary layer or for clouds. And you would be using. In today's world, we have lots of data coming from various sources, satellites, etc. So we can use an AI/ML technique which could replace, let's say, your image parameterization or boundary layer parameterization. You use still the conventional numerical model, but you replace it with the AI/ML model within that. So that's what we call as a hybrid model. Then this is a new thing that is coming in, which we call as digital twins. I talk about Nanjundiah. Data-driven. Okay. One thing we need to keep in mind, in today's world, we think, okay, when I'm using a data-driven model, I just click on a PC and I get a forecast. But what's going on behind it, we are not very familiar with. They are highly energy consuming. Let's say, even if you are doing a search, let's say on WhatsApp, now WhatsApp gives you a search. It's highly energy intensive. We don't realize it, but a lot of energy gets wasted, especially in data centers. Data centers are one of the biggest, you could say, consumers of energy in today's world. So, but the advantage is, once you have trained your model, you will get a code. Let's say you're looking at a data-driven model. You may get a result on your PC, running on your PCs. Something compare PC. Okay. One of the things that we are seeing, or let's say I have read, but I'm not sure, is that once you have trained your model, that is basically what is what's the data-driven model? In some sense, let's look at the regression. You have A, B, C's, etc., etc. Now think of it in a million parameters. That's nothing but your data-driven. Of course, it's one unique, it's one minimization, more fancier techniques. But once you have trained it and you're going further from the data that you have trained, let's say I've trained it up to 2000. And I try to compare the forecast I get in 2004 as compared to, let's say, 2024. It's quite likely that the errors will be larger in those forecasts in 2024 as compared to 2020. If I have frozen the data at 2020. Maybe at times we may have to keep tuning the models or retraining. So also let's look at what are the quality of forecasts. Okay, sure.
Space on database accumulation.
Let's say, look at the data regression. Finally, you're going to optimize with alpha, beta, gamma, or whatever you do. So that's what in a simple example.
So if I understand this right, we have not data acquisition. I will take in those different dimension space. We are trying to fit a plane in which we are trying to find an R scenario format and try to predict what would be the variable output for that. So when we talk about points which are further away from the already seen data sets, to approach those points, can the model also incorporate physics?
Well, I mean, that's what we use these models. Uh, I mean, let's say, even if you're looking at purely a data-driven model, let's say I have trained it with 2020, that we know that, okay, that over this one, decadal variability, etc., which may not have been captured in the last 20 years. So that itself would be contributing to a kind of a drift away from continuous drift that we're looking at. That would be one possibility. Secondly, I mean, possibly the climate is also changing, which also will say that, okay, what I trained in 2020 may not be accept correct today. So that's also possible. So your errors might increase. Okay, and purely data-driven models, not a physics. That's one of the things when you are looking into the future. That's one of the major, you could say, disadvantages, for especially for climate change studies. Because whenever, in some sense, data-driven, what is it doing? It's looking into the past and saying, okay, this is the feature I have found. So this is the most likely feature that I'm going to get. And that's what it's doing in prediction. They are very, very simplest. And let's say climate change or some scenario which it has not seen before, it's likely to fail. Okay, so we did some tiny experiments a few years back, so as to predict the mean monsoon. And the inputs we used were simple, 10 meter winds, 2 meter temperature, etc. in sea level pressure. And we used what we call as a stack encoder. In simple words, it would say in some sense it can be nothing but a traditional reduction technique. We have data from all these variables for various months. Let's say you take 5 or 6 months before, let's say when you are looking at JJ, you would take data typically up to, let's say, April, when you do the forecast. Take the 6 months data and use it to train your model. And what the encoder would do is it would reduce the dimensions of it, pick up the main features. Now, once you have these features, you kind of look at its relationship with the Indian monsoon rainfall. We used simple correlation. I'm sure there are better methods also to look at for these relationships. And then we use it to do the forecast. From that, we pick up the major variables. And then you see how good the forecast is coming from that. So that's what we did in a very simplistic way. And if you want to understand, this in a sense is what exactly we done in bigger models also. You have data coming from various sources, which could be reanalysis. Here, of course, we use NSEP reanalysis as data because it's quick and easy to use, and we were looking at way back in 2018. So we thought it's easier to use NSEP at that time, but today you can use data. And if you're looking at the bigger models, that's what they are doing. If you look at graph paths, the flow is the same. We have an encoder, which in some sense picks up the major dimension, then kind of translates it to within the area that it's looking at. It's slightly more complicated. Finally, it looks up builds the relationships, and those relationships it uses to the prediction. So in a sense, this tiny model in some sense abstracts everything that today's more fancy models are. Okay. So let's see how well it did. So using these predictors, we got errors which were of the order of 4.4, depending on various sets of predictors, atmospheric temperature, SST, SLP. So we got those kind of errors. If you compare it with the IMD model, which is the model which they have still been used, in addition to the numerical model, its error was 7.5%. And so if you compare it with, you're getting a much better model. And this is the comparison with various, this is with the various combinations that we have used. And you can see that it's doing much better than what the model they have used, the regression model they have used. And if you compare it with numerical models, the temporal correlation which we got for CFSV2, which is the forecast model currently being used by the numerical forecast model being used by IMD, it has a temporal correlation of 0.55. And from various other sources, which Ravi had calculated was 0.45. Of course, these results are a little dated. I'm sure it has improved over time. But still, I don't think they have come to the level where a simple model had correlations coming to 0.8, 0.2, 0.8. Just with the model which runs in.
Sir, I want to ask you, do you think SLP alone will be the highest correlation? Is it?
There are yeah. He did a lot of combinations.
Yeah, but
Finally,
highest is and use only SLP. Is that what you mean? Or combination?
No, this is only with SLP. You got a 4.4.
Then also 0.83 also is SLP.
I think it's SLP. We looked at the best results. It should be done. Yeah. I mean, we have looked at various combinations. We even looked at kind of a non-linear combination. Let's say we multiply AAT with SSP or AT with SLP.
They don't go better than this.
They don't seem to be better. Or I think so. You know the best model we saw.
Multivariate regression will not yield better. A single variate regression.
Well, I mean, IMT is multivariate.
I mean, here when trying to take this correlation, is it like with respect to just SLP alone, SSP alone, and
No, I think we tried also combinations. We have tried.
is that better than individual?
No, I don't. I mean, in this case, maybe not. Maybe, okay, there were a couple of things we did. Maybe in this particular forecast, we may not have done a combination of them. But in one of them, I clearly remember that a combination did give a better result. But maybe in this case, we have not done. Maybe it's possible that you could use a combination negative because in some other thing we have used a combination. Maybe it was for regional monsoon prediction or somewhere we got a combination which was going better.
So in the second rule, as a statistical model, second rule in the
Yeah, that's the statistical model. And the CFS exact errors, I'm not been able to find. It's nicely written somewhere, I'm sure. But if you look at the temporal correlation which they have reported, it's 0.55. The same temporal correlation, that is over the time period for which you have done the forecast, we are getting a 0.81, they are getting it. So in that sense, it's still doing better than India. The area of correlation, I'm sure it's somewhere there, but I couldn't easily get it. I mean, a single number which they have done in comparison, I'm not sure. Because they do have problems with the trials. So they can get the rainfall, I think, is much, much lower. So the error itself will become much larger if you're looking at in this sense of a single number that way. Of course, there is a thing that if you're looking at something like a seasonal forecast, it's giving you many other parameters. This is only giving you one parameter. So it's not a fair comparison. But if you're looking at only the forecast as a single number, this is a good thing. We can dirty way to kind of look at what might happen. Let's say 5 or 6 months before we stop with predictors with only up to date. We can take data from beyond to do these forecasts. So we did a prediction for the various homogeneous regions. And these were the various regions of the world which kind of combined to give you the first forecast for various parameters. And these are the homogeneous regions where we looked at it and how it compared to, let's say, the IMD predictions. So you could see that the numbers were similar.
How many years you're comparing?
Whatever data we could find from one. And for us, I think we did comparison from 2001 to 2014. That's the data that we have. Of course, forecast whatever they give because we don't have the actual numbers for that. But whatever they gave us the numbers for prediction, we have used that. But the period where we have done the forecast, I think we trained it from 79 to 2000 and did a validation from 2000 to 2024. So, though we got good results for seasonal meal, we also tried for active and break, which in some sense is the sub-seasonal variation, and which WMO itself says it's the graveyard of predictability. When you're looking at short range, it's driven by initial conditions. You get good forecast. In seasonal forecast, the guidance coming from the ocean is good. So you get reasonably good forecast at that. But in between is a kind of a dicey situation, a gray area, which actually they call it as a graveyard of predictability. And that's what we thought. We'll try to look at active and break spells. I'm sure all of you are familiar with it. Jess has been talking about active and break spells for a long period. So basically, what means is that you have periods of intense rainfall, kind of in between you have periods of no rainfall. So that's the active and break spells that we look at. And that's what we were trying to predict using a technique called convolutional neural networks. So the variables that we used were winds, temperature, and rainfall itself are one of the variables. Then these are the other details which we get. That is, you take the data, again, in some sense, it is a dimension reduction we are doing, running it through all these neural networks, get the active yes. So these are the, and when we looked at the inputs, we knew that will certainly have an impact. So we used it as one of the inputs. In addition to the variables, the winds, the geopotential height, sea level pressure, and air temperature. In addition to that, we said, okay, we know that this kind of effects both are active and things. So we use it, and we also know that masculine height can play a role kind of modulating the strength of the monsoon resistance. So these were the variables that we took. And okay, there are a series of numbers. All I would like to say is this was the previously reported result, which is self-organizing maps. And compared to that, we got a 54% improvement scheme with that. And these are the other techniques that we have used. One of them is the long short memory technique, and linear discriminant analysis is another technique. So CNN gave us the best combinations of it. And of course, what we found was we could do active spells better than break spells. Normal spells are not of any interest. You say everything is fine and it's fine. You're not interested. Okay. But the data, the skill is still modest as compared to what
Are you predicting the onset of break and active or duration? What is
the duration and the magnitude.
duration?
That's I think what we are finding is because now also I think Ritesh is still looking at it. He's still having problems in kind of improving these results. It's still a major problem for us, and I think everybody looks at it. Like for example, the recent work which Krishnamurthy and this group, George Mason, they have used MSSA taken the MSSA, the long run high frequency and low frequency, initialized with CFS and trying to do a forecast. And they say, but only for those, they are not actually doing the numbers for it. They are only seeing the patterns.
For the first 11 years of this period, how many breaks and episodes you have? Not too many, right? There's a problem with numbers here.
Okay, no, but every year you'll have at least 2 or 3 breaks. Any long breaks.
Yeah, if you example is about 2025, that's what.
Yeah, but even if we went back to 79, now we are using data up to 2018, but we are still finding the same problem. And I think most of whatever I'm finding in the intra-seasonal scale, the good results that you get either on the short range, like the GraphCast they are now talking about, or the seasonal prediction, which we are doing very well with data-driven models. We're not able to do that with the intra-seasonal scales. The skill kind of rapidly reduces as you go after about 5 to 7 days. This one. We tried some experiments. Because this larger region was largely insensitive.
To extend it more towards the north, would it affect your prediction capabilities?
I'm not very sure. I'm not very sure, but I mean, like my postdoc, she did, I'm sure she did quite a few experiments, fine, till we kind of zeroed on the area that we're looking at.
This is data is not physics. So the data points that we're going to give is going to either induce noise or would lose the signal.
It's possible. I mean, she must have played around with the region and then said, okay, this is the best region, which I'm getting the best performance. If you want, I'll give you the reference of it. All the gory details are there. So now I'll come to GraphCast, which is Google's, which is, I think a lot of words are being put around for that. Again, if you look at in this conceptual way, you have the input weather state, then you predict the next ride and you roll out traffic program, which is very similar to what we do. And if you look at it as components, you have what we also said previously as an encoder. Then you have the processor. So encoder takes data, let's say from ECW, puts various features, and instead of using the flat surface that we do, they kind of project it to a microsecond at various levels. So you start from a very coarse level till you come to a very fine level. So if you're looking at this particular point, it is kind of looking at a very fine level. But at each level, they try to build relationship at coarser and finer levels using one of microsecond. So, and that I think this is I think they use a GNN for this purpose for the encoder. Then I think they use a 16 layer, the processor is a 16 layer GNN, which is a neural network in sense for us. And it kind of builds relationships. So it is a massively parallel technique they use. So for that, because they would have decomposed the globe into various pieces. If you look at icosahedral, in some sense, think of it as a football in patches of it. In some sense, if you look at this, it's nothing but football. If you look at finer and finer pieces in football, it starts looking like a stick. Okay, so that's what icosahedral is. And from that, they build up the relationships over different parts of the world. And the inputs they are using is nothing but temperature, winds, and I think specifically those are the inputs they are taking, and they are taking it from ECMWF field analysis at 25 kilometers. Okay, so then the next one is it gets all the feeds to the input, and then it kind of creates a forecast, which again goes into this kind of a dimension which we may not be able to understand. So you have the decoder step, which converts it onto the sphere and the baby. Okay, so this in some sense is the crux of the GraphCast, and other techniques, this particular central thing may vary from one technique to the other, from GraphCast or PodcastNet. But broadly, the same flow is going to be adopted in the other data. Okay, so these are the other details. And one of the things we always find is data-driven models have difficulties in quantifying the uncertainty. If you want to do an ensemble prediction with data-driven models, the nature of the model is such that you are minimizing the error. So it is kind of hugging the mean in some sense. So you're not able to give a spread and create an ensemble. So that's the problem with almost all the data-driven models, which seems to have been kind of slightly overcome from the latest one, which is called as the neural GCM. I tried to talk about it in it. Yes, I'm getting late. I mean, am I taking too much of time?
No problem.
Okay. So these are the errors. This is the skill. They are compared it with the ECM. So this is GraphCast, and this is the RMSC for ECMWF IRS. And this is the skill score. They are kind of, it's a normalized skill score with ECMWF. And the break they are getting is because I think they used one set of initial conditions. I think from 0, they picked up forecast from 6Z and 18Z. They switched it to 12Z and 20Z. I think there's a changeover in that the data. That's why you get this kind of discontinuity. But what you can still see is that it's normalized scale scores. If you take ECMW as 1, then graph class will get your skill score, which is much smaller than ECM. Okay. Similarly, we are looking at what's called as the anomaly correlation, which is like the gold standard to check if a model is doing better. That is a 500 hectopascal geopotential global. So you find that this does much better. The graph class does much better than ECM. So this is what we are showing. And these are various variables. The lighter the color, the better it is. The darker the color means it is worse. And in almost all of them, this red means it's a one-dimensionalized one with respect to ECMWF. So that's why it is red. The lighter color means that okay, the errors are smaller. And these are various variables: 2 meter temperature, 10 meter winds, and least level. This is what it means. Yeah. Those are single level variables. This is specific to 3D temperature, geopotential, velocity, and wind, wind at different levels. So you can see that in almost all the levels, graph class is kind of doing better than ECW.
So Ravi, you know that what region is this forecast?
This is global. Okay.
So I wonder that if they do it for over small regions, then the models will be better.
Just give a minute. I'll show you one small example which we did. Okay. These are the, let's say, atmospheric rivers, which in our simple, for us, in India, it would be nothing but your westerly jet. That is, you have a strong flow of wind, which carries a lot of moisture, which is nothing but your westerly jet. And I think they have looked at, in a global sense, atmospheric rivers and cyclone tracking. The graph class is doing better with less error as compared to ECMW errors. And even for atmospheric rivers, it is doing as well as the European. And this is one recent example from data. This was the Hurricane Beryl, which hit, I think, on 1st of July. And on 1st of July, they took the forecast was given by NSEP and ECMWF. So this is the ECMWF path for it, as forecast on 1st of July. And this was the NSEP forecast. And this was the actual path. And on 1st of July itself, graph class gave the path to be this. While if you look at the American and the NSEP and the ECMWF, they were showing the track to move more towards west as compared to what we found. It was a recurring thing which we didn't capture on first. But if you look at forecast from 3rd onwards to ECMWF, it was able to capture the recurring. But even with 1 week or 5 days lead, the data-driven model, graph class in this case, was able to get a fairly good.
What do you think of a spread? I mean, is this their best case or is there a spread in that? Do they give a spread, their forecast?
Maybe they have. I mean, actually, this is from New York Times.
Yeah, I know.
I mean, Gopal gave it to me, but you can see
the best case for yourself. Because both of them would like to look at the spread of the forecast to get an idea of what's going on.
But I think they have, this might be the best track they are showing for that.
Okay.
Maybe some mean of the track that they are talking about. Since
No, that is the example B because of.
yeah, these are the example.
Yeah.
Graph class this is purely deterministic.
Okay.
And
Okay.
as I said, the spread in graph class would be very low. They are not able to get the ensemble spread. That's one of the major problems with data. I'm sure that this might have some errors, but since it's a popular article from New York Times, So I think cannot be one spread for individual models.
Spread is better.
Huh?
Spread is better.
I mean,
Secondly,
uncertainty is also good, right? I mean, let's say if you're going, your deterministic model is going on a completely wrong path, then spread kind of gives you a warning that, okay, things may not be all that correct.
people don't want huge uncertainty. We don't know.
That's true, but at least you know what's the probability of occurrence. Let's say as the mean is concerned. If there's a large spread means, okay, less certainty about the deterministic forecast. So there could be, it could be less certain. Let's say if it's giving you rain at time day, and it's in the 50% chance that the 50% of your forecast of see is rain and 50% don't, then the probability of occurrence, possibly the probability of occurrence would be much lower. Okay, so I think to answer your question, we looked at forecast net data. My student current, we looked at global temperatures, which is only a 5-day analysis. A lot more work needs to be done. But what I would like you to say is, this is the era data, and this is what the forecast net is giving. Just for 5 days. One example, I'm not saying that this is true, but you can see that there's large errors when you're looking at the global mean temperature. It's not as rosy as we would like to.
Now, what I predict here?
It's only the global mean temperature.
Temperature. Okay, easy one.
Yeah, I mean, the grossest one that we wanted to look at it, we had a very small data set to look at. I wanted you to kind of get a speed quick on this.
What is rainfall? Rainfall is more challenging. Is that okay?
Yeah. So, and these are the difference in temperatures, which if you're looking in a global sense, it's okay, but still you're getting errors, which, okay, not very large. This is 273.9 and this is 273. So about 0.5 degree difference is what you're getting, which in a global sense is okay. But if you're looking at locally, there are large errors. You can see the temperature. In the global sense, it looks good. So we looked at rainfall forecast for India, and this is of course the global difference of rainfall. You can see the errors are much larger before, as compared to, let's say, temperatures. And this is the GTM data which we have compared, and this is the forecast net. And you can see this is a 5-day forecast that is
The All India mean. The All India mean, what are you showing?
this is All India mean 5 to 25, not 60 to 9. And you can see there are large difference. This is the forecast net which is getting. This is the GTM net. So rainfall is still a challenge, and this is the map of rainfall average over time. So digital twin, I think yes, I'm taking a lot of time. Shall I? Would like me to skip it?
No.
Huh?
Go ahead.
Okay, I mean, digital twin, I think there's a lot of buzz. It basically is like combining data and kind of on the fly kind of motion. You take observe data, or let's say if you're looking at in general a system, you're getting a digital twin. As the data comes in, you can do the correction of simulation. So there is a difference between simulation and digital twin. I'll come to that in a moment. And this is in some sense you have simulations, observations, which the two major digital twins for climate is I think Earth 2 and Destiny. Destiny is from ECMWF and Earth 2 is from NVIDIA. I think I'll skip this and okay, this is one example of a digital twin which I think we should look at. Now, if you just look at the left-hand side of it, forget the right. I'm just looking at CO2 emissions as the input. So what I'm doing is nothing but the scenario simulation that we do. Now, let's say I bring in the right side, this call as a human system. This is called a PSM from Department of Energy. And you also keep putting in inputs of CO2 emission and you rank over as the model simulation progresses. And the feedbacks are taken into it. So that in a sense is for us, as far as climate change is concerned, is a digital twin. That is, you have, I mean, if it was a regular simulation, I'll say CO2 was fixed on some particular rate at which it's going to increase, or I'm doubling or whatever. But I keep it fixed. I don't kind of tinker with it. But let's say I build this part of the model, which they call as the human system, GCAM, which kind of gives inputs continuously to your model and modifies the trajectory which is going to. That means it's continuously giving data. Now, if I'm looking at a physical system, let's say you have a sensor which will be giving you data, and it will be looking at what the simulation is doing. And let's say you're getting temperature or anything, let's say wind or whatever, and you can continuously correct your simulation that you are doing. In this case, that's the input that we are giving to it. And this is what would be a digital twin in a very simple state.
How is it different from climate change?
This part is cut off.
No, I think we don't give future.
But on the fly, you don't. Once you give it, you be able to fix it. Or you kind of prescribe it. In this case, it non-linearly interacts with it.
Oh, so this is giving feedback to.
Yeah, it's the feedback. That's the idea. You see that there are feedbacks. For example, if you take terrestrial relativity to go into land, you'll have CO2 emissions which will come into the model. And then you have relationship between land, water, economy, energy, policy, all of them come together. Depending on how you tinker with your policy, the whole policy change itself, you would be able to change this. This part is built. I think they are building the right hand side. This is the Department of Industry E3 with GCAP as they call it.
If I understand right, digital twin would be like something like data is in the state of the earth, which with the future scenarios, people show me the power.
Possibly in future scenarios, if you're looking at climate change or digital twin for climate change, let's say you're looking at an nowcast. And in the present forecast, I'm going in time, I get additional data. I can modify the forecast itself on the fly. Let's say I go, let's say a 3-day forecast. As I go along and I want to do it for the next 6 hours, I get more data. I can change the trajectory of the forecast that I need to get the forecast. So additional information as it comes in, I can modify. That's the difference between a digital twin and a regular forecast or simulation.
This is one more level of thing itself.
I mean, for this one, I mean, digital twin is very. So this is I'm saying as is possibly a good. I mean, try to kind of simplify it and say you it is a digital twin, though they don't call it a digital twin. But as far as if you read about that, it almost looks like a digital.
It's like the present state of the. I mean, I'm just trying to understand this. So it's the present state of the earth presented in data. You have the capability to project it for let's say short time scale.
Yeah.
So it's just a step higher than analysis, what the analysis is doing.
Dynamically, it is changing itself. It's changing its own state. Let's say we look at energy, economy, all of them. If economy is going to go down and energy consumption will go down, CO2 will go down. So that will kind of feed into your model.
If I
And if that again will change on this, and there could be a feedback which could be coming. I mean, in a very gross way, I'm talking about it. How do I go back to Sujata? Oh, here. Okay. This is go back here. Okay, so this is more details of the digital twin which I kind of skipped for from CMW. So it can operationalize the assessment. All the other details are there. I'll leave it to if anybody is interested. Sure.
When we project the climate change, it is usually for a longer time period, for maybe 50 years, 20 years.
Sure.
So at that time, even these externally the feedbacks which we are talking about, that can be
Yeah, but I have to wait 20 years. I can do a what if scenario, feed it as the model is going. Let's say I started my model at 2020. The model is going into 2050, and I see some, I can say that, okay, the economy is changing, etc. The energy thing is changing, the emissions are changing, which on the fly it kind of corrects itself and gives you a forecast. So the trajectory itself at each point, let me see if I can go there. Oop. Okay, in a sense, you may have a fixed trajectory over which it is going. You can continuously modify it. The trajectory itself, because you have feedbacks coming. And if you're interested, more details are available. I'll put the references for it. Yeah. It's a very good paper. It talks about digital play. It's basically what ECMWF is using. So these are the questions that you sort of you asked. What's the difference between a digital twin and a simulation? Both of them are digital models, which look at various processes, but one has a feedback, the other one doesn't have. It's more like a static one. I mean, there are other details which I'm not doing. It can be looked up here itself. So this is one which I would like to mention. I think as far as data-driven models, at least as far as I think, this is one of the biggest steps that I'm seeing. Up till now, it was purely data-driven. Not much physics was going into it. I used to give some data. It gives something that it may violate physics, it may not violate physics. You can know the thing. But in this case, what they are doing is the same data is being taken. This is in some sense a very gross sense a conventional model, which has a dynamical core. It also has a physics. The difference is you are using neural networks for the physics, and also dynamical core is conventional. Let's say you're using the spectrum system. And then you keep solving it. Let's say you take this input. Let's see, in this case, it is the ECMWF. Encoder again is kind of converts it the way the model wants it. Then you have the dynamical code, learn physics. Then at the end of it, the tendencies of physics, let's say the change of temperature, velocities, they come. And the physical tendency, let's say the heating terms, that come from the physics. Let's say cumulus heating, radiating, all of them, they come from the learned physics, which itself is a neural network we use. Combine them to an ODE solver. They keep kind of iterating here. And after, let's say, every 4 hours or 6 hours, when they're training the model, not in the forecast mode, but in the training mode, you take data from, let's say, ECFW of pre-analysis, compare how far it has shifted, correct it in some sense the error minimization, and send it back. So you keep training it. So they are training it for a period of, I think, 1979 to 2018 in chunks of 5-day code bursts. And if you want to do an ensemble, what you do is you add noise to this. So you can create an ensemble. You are using a similar model. So you're kind of creating noise and putting it into a system. In that way, you can even create an ensemble. Okay, so that's an advantage which you get in what's called as neural GCMs. It came back, I think, 2 weeks back. There's a paper in Nature, and last week there was, I think, a comment in Nature about this neural GCMs. And it looks the most interesting thing as far as I can see. These are other details. They use a language called JAX, which allows for automatic differentiation. That's a technique where you can look at the differentiation on the fly. That is, you get a variable, you can do a differentiation of it. That's allowed in JAX on the other details. Okay. So they trained it on ERA data, and for models as coarse as 2.8, 1.4, and 0.7. And these are other details of it. And they have done a image style simulation. Yeah. We are not looking at future, we are looking at past. And for the higher resolution, they use this data. And unseen validation was in the 20. And the feedback that I said, they varied between 6 hours to 1 minute. Initially, I think they started with 6, and as they went along in the period from 1979 to 2019, from what I read, it looks like they increased this period of where they would connect the data, the reanalysis data, with the 4 months. Okay, so these are comparisons. This is the RMSC of versus climatology of specific humidity. This is for ECMW of ensemble. This is for neural ensembles. You can see they're comparable. This is specific humidity biases. This is specific humidity CPR. That is how we put the spread is. And this is another specific humidity, the spread in the scale. So you can see that it's fairly well spread as comparable to. So if you compare it with ECMWF, it is comparable. And interestingly, the closest resolution they have taken is only 0.7 degrees. While ECMWF runs at about 10 kilometers or 6 kilometers. The short range forecast. And I think they also compared it with the GraphCast and Tango, and it's doing much better as compared to GraphCast and comparable or better than ECMWF. So these are tracks of cyclone from ensemble at 0.8. Neural GCM, which is run at 1.4. So you have a good spread, which you can see here. And it's comparable to what you do with an ensemble at ECM. And it's highly efficient. Of course, if you can lay hands on a tensor processing unit, which is proprietary of Google, if you get it, I think, then you can do 200 years of simulation in a single day. And results at 100 plus kilometers is comparable. And here, this is, I think, a comparison of a particular day, where you can see that this is estimation from data. This is ECMWF. GraphCast is much more fuzzy, and you get a much better picture with the neural GCM, even though it's running at about 1.4 degrees. So they have done AMIP style simulations, and this is the change from 1980. This is from the AMIP models. This is from era 5, and this is from the new images. You see that it's very well, very well, and better than what the AMIP models said. Of course, we have found that there are problems. They tried a simulation where they tried to put a 4-degree surface warming and model gave crazy results. That's what they said. So obviously, what it has not seen before, a 4-degree warming it hasn't seen. So it's still not able to capture it. But for others, it's able to do. And I guess if they can find a better way to train the physics of the model better, I guess this would be the way to go forward in it. Okay, so that's it. And these are some references to those who are interested. Thank you.
Any questions?
General question, just want to know your opinion. Suppose, let's take two scenarios. You do one dynamical model simulation of basically a cycle, and then the same you do data-driven model. And the data-driven model performs better than the dynamical model for one particular site. You did the same for, let's say, another cyclone, the dynamical model performs better than the data-driven model. So, as a scientist, what would you choose to improve the parameterization, which might include the cyclone transports, or go on the data?
I would rather go with the statistics of it. Let's say, in general, what are the statistics? Of course, there will be deviation like this, again, ECMW does very well most of the time. In this case, graph casting. But I will still go by the statistics that, okay, if ECMW is doing better, then I'll have more trust in it. That's where you can do even a multi-model answer. So, but I mean, it's again, you have to kind of look at it, do it. You cannot say that, okay, in one case, graph class is better than the slow graph class. Can't completely do that. And we know that there are limitations with graph class. If I wanted to look at that, let's say pool of uncertainty. What they have seen is the best track perhaps. But the pool of uncertainty which is usually generated when you're looking at a cyclone, you want to know where the, let's say, the landfall is. We may not be very sure. So you do ensembles. I think graph class is good. It's not a good bet ensembles. I think that's the only place where, let's say, data-driven, semi-data-driven model, like a neural GC might do better than a pure data.
Yeah, I have a question, like, what is this one? See, we know that these areas in the models, right, our dynamical models, most of the error they get from the physics.
Yeah.
Isn't it? So the reanalysis is the function of the physics, error in the physics. Any error in the reanalysis is a function of the error of the physics, mostly, given that data is at around the same time. So it will be from the data or data collection or right? Now, in these models, that including the digital, especially digital, for example, that we are training the models physics, which is a digital twin, right? Dynamics is the dynamical code, the dynamic whatever it is, isn't it?
Yeah.
Using the data set, which is in analysis, which are itself as error. There's a completely contradictory.
Well, I mean, what you be the nature of it.
Saying that, what I'm saying
I
that.
mean, if you forget on, okay, let's say I have ECMW analysis. The best I can do is go to some analysis and compare how well the forecast one is compared to that. That becomes a completely different calculation. Otherwise, how do I train it with the data? The best data that I have is ECMW.
I agree with your this one, but
Yeah.
what I'm saying that is the philosophy of developing a model to physics from a data set which itself is faulty. That's what I'm trying to say. Isn't it?
It's all that okay, let's take it. Satellites are better. Satellite data that they get to the weather. So, I mean, we have, let's even with the analysis, we have an estimate of error. And you're also running your numerical model, which again, it sounds as initializing with the same computer. And but remember, in the training period, once you have created, no input goes into it, just like in a numerical simulation. Let's say in style you do, you started, let's say, from 1st January 1980 and continue with it. That no initial data, other than the initial data that you have given, no input goes in, no additional input which you don't have given. And of course, ECMW analysis is built on a model. So whatever error comes from the model physics will all be there. And what you are trying to do is, okay, this is the true process to do. So I'm trying to minimize the error. That's the only way I can do that. Unless you get another source. And then you compare it. Let's say I use ECMW and then I say compare it to satellite data. That would be a and completely independent of the language. But that's the only way we can do it. I know what you're saying, but
We used to have this TCAM, right? TCAM is like economic model, basically social economic. Yeah. So in my opinion, they also used to have what's called integrated assessment model, IAMs. They used to call this as IAMs. Okay, so IAMs are basically, they had very simple climate model, but very sophisticated economic. But to me, it looks like this within basically sophisticated economic model, pretty sophisticated.
yeah, because what yeah, now you have a XLP computer.
Yeah,
So they want to make it and then you have putting in more process.
It's my observation.
Yeah, in a sense, that should be increasing the complexity of the system.
Ravi has asked that, can you comment on the conservative quantities in training models?
By nature, they may not. because any graph kind of, I don't think it conserves. By default, there's no physics constraint, which is there in the numerical progression. That's a neural sequence. You have physics constraint because they're running both the numerics and dynamics together. So there will not, that will be consistent, but this will not be physically consistent. You may not force that consistency.
Abhinav, is how would you go about contrasting events like fog using such models? Specifically speaking, the historical data itself is not available or scarce here.
Okay, I mean, okay, let's say, okay, we don't have much data for that, so we can't give social data. But whatever data we have, we can, I mean, there are observations, let's say for IGI report, there are now 5 years of data, which is being collected. So using that data, you can build a simple model which could be only specific for maybe around Delhi. Or maybe if you have data for a larger region, then you use that and feed the data into the model. And also use indirect parameters. Let's say you have RH and you have temperature, profiles of temperature, you bring that into it, and then you kind of do a data driven model. There will be errors. Even today, even if you look at a fog forecast today, let's say what is being issued for northern region, they have huge errors, which could be as big as 100% error. They, like the one forecast they give, it has a tendency to over-predict. And there are problems with humidity which is coming from the numerical models. They are using from that. So there are issues. And even if I'm using a pure numerical model, there are issues.
So, okay. Short presentation here. Sorry. Yeah, it's hard here. Yeah, Monsoon is going quite well. But one part which I want you to notice is what is happening in the core monsoon zone. The core monsoon zone for the past, I would say 15 days, are not looking very good, okay? Especially here. So, but we look at the all India rainfall is doing well because east and northeast are getting more rainfall now. So all India is very misleading. There are a lot of rain in Kerala, I think all India is good at not. So this is very surprising. We'll see what happens in the next few days. But yeah, monsoon has peaked, but all India monsoon rainfall is still 3% above normal. Okay, that is.
Usually, you always say that there is a climatological break, which is
Yeah.
So this also is something we get to that particular kind of
Yeah. So the north rain is related to break and rains. Yeah. So this I'll skip. I just want to remark about what happened on Monday. On Monday, I got caught in the such a heavy rainfall at 3 p.m. How many of you remember it? I was in the next building and I couldn't come out here. This distance. And it was, I've not seen such intense rainfall done for a long time. So 1 hour it really poured, okay? And the tunnel was flooded and so on. So I was curious to know how much it rained and what the forecast was. Now, what's interesting is that the case Karnataka State National Disaster Command Center forecast next day's rainfall based on mesoscale forecast provided by Space Application Center Ahmedabad. Okay, interesting exercise. I wish more people would do it. So they predicted on Monday morning or Monday by 8:30 a.m. or Tuesday 8:30 a.m. that Yelaka region will get 100 millimeters of rain. Okay. It didn't come out right, you see here, but if you look at the pattern, they were right. It rained more in North Bangalore and ISC somewhere here than South Bangalore. That got it right, but the rainfall they got it wrong, actual amount. They had done a bias correction, maybe they would have succeeded, I don't know. But I was impressed that they did say North Bangalore get much more rain than South Bangalore. And we did get actually highest value they claimed is 30 millimeters, but I'm sure in IAC, I'm a second whether he has data on the roof. I'm sure it's more than 40, 50 millimeters. So this forecast is not bad in terms of spatial patterns, but the amount was wrong. And what did I get it?
About 10 centimeters. With what is about 10 centimeters.
No.
Can
I checked with, I'll tell you, I checked with ISRO into 30 minutes estimate from satellite. That is very evident. But you know, that's an estimate. That's wrong. You can get half an hour for it goes a peak at 3 p.m. and then comes down. Very nice, but number is not right. Now I want to compare with what IMD provided. So that was state government. IMD provided rainfall on morning of 28th, almost no rain in HAL airport, 4 millimeters in Central College. This is not bad. Okay, so that gradient is correct. There was a huge gradient of rainfall, and so this is correct. And so Yalanka was somewhere in this region, but ISRO showed 100, close to 100 millimeters.
Yes.
Yeah, GKVK is a bit surprising. You're right. GKVK bothers me. It's about 10 kilometers from here. That shows you the spatial variation. I mean, that is the part which no model can capture, right? In IAC, it's 50, 60, and GKVK just as the crow flies the 10 kilometers. So, yeah, that is surprising. Unless there's a problem with the gauge. If you ask Buddy, we tell you, rain gauge maintenance is a critical issue. If you don't clean a rain gauge, we get zero rain. So that's the problem. So I'll skip. I think that I have to show here. Yeah, I just want to show what work was made about 3.4 on 1st April. Okay. Most models gave numbers around -0.5 in August. We have finished with August, it is 0, not -0.5. 3.4 is still high, on 0. So that forecast was quite wrong on 1st April. So we'll see next week whether it will change or not. Okay. And this was, sorry, this is the old one. Yeah. I think I didn't have. Yeah, I remember that the forecast for last week was plus 10%, actually was minus 10%. For this week, it is plus 30%. I don't think it's right. I'll tell you next week what the actual number is. So these two forecasts are not coming out right. Okay. So I'll stop there, and next week is Mahendra. Okay. This is yours. Yeah. I mean, they can